page 9. Okay, let me start off by building a foundation of area first, and then from there we can kind of see the connection between area and volume, well, at least the volume that we're going to be working on. So let's just say we want to find area under the curve y equals square root of x. So square root of x is here. That's just the radical function between 0 and 4. So between 0 and 4. So there's 0 and there's 4. So here's our shader region. And if we want to find area, we're just going to be going through this formula, right? Top graph minus bottom graph dx. So we can do vertical rectangles here. So I'm just going to draw one representative rectangle, but the idea is that there are infinitely many rectangles, infinitely thin, extending, you know, from all the way over here to all the way over. But this is the orientation. They're all going to be vertical rectangles. All we need is one rectangle, one integral formula, because the top of every imaginable rectangle in this region is hitting the same graph, and the bottom of every imaginable rectangle is hitting the same x-axis. So let's set up our integral formula there. So area is equal to definite integral from where to where? 0 to 4, x values, these are all x values. Top graph, what's the graph on top? Root x minus, what's the graph on the bottom? 0. Yeah, this is y equals 0 here. Yep. Okay, I want us to. I know I've talked about this already, but I think this is a good connection point, especially with volume. Is that we understand what that root x minus 0 is representing, right? It's representing the what of the rectangle. What's it representing? Okay, close. The what? The dx is going to be the infinitely thin width. But the root x minus 0, this minus this will represent the what? The length or the height. Okay, all right, it's fine. So hopefully we see that the area component of the rectangle kind of forming within this integral formula. So let's go through the process. We can go through power rule and work our way through this, right? So root x, the same thing as x to the 1/2. We go through power rule, x to the 3/2 over 3/2. It's really 2/3 x to the 3/2. And once we have our antiderivative, we can evaluate between 0 and 4. Upper bound minus lower bound. So 2/3 times 4 to the 3/2 minus 2/3 times 0 to the 3/2. And all that is going to give us 16 over 3. We're talking about area here, so units squared. Okay, all this is review, but there is a nice connection point between this and volume, so I wanted to start here. All right, so essentially the integral notation allows us to add infinite numbers of differently sized rectangles to form the area calculation. And the differently sized rectangles, different heights of every rectangle is accounted for by root x minus 0. So root x minus 0 is going to keep adjusting to all the different heights across this entire region. Okay. All right, so this is the exact area of this region if we were to add up infinitely thin rectangles from one end to the other. So now we're going to take this same shape, okay, and now we're going to create a volume problem out of it. Okay, so volume is a three-dimensional calculation. This is only two dimensions. Okay, so three-dimensional. We're not going to really have to draw them, but for now, I just want to kind of show us so we can kind of have some perspective. So with this method, what we're going to do is we're going to take this region that we created from f of x. Okay, so the same region that we have here, as above. And now, instead of just finding the area of this region, we're going to take this region and we're going to rotate it 360 degrees around the x-axis. So imagine taking that flat surface and rotating it all the way around until it forms kind of a bowl-shaped object in this case. Now, because these are rotated, what shapes do you see that comes out of it? Or if you were to slice this in half and you were to open it up, what shape are you going to see? Circles, right? So that's the idea, right? Because we're always rotating 360 degrees, we're always going to get these differently sized circular discs, okay, circular discs, and that's what we're going to be kind of working towards. So now, instead of thinking of it as, oh, I'm adding infinitely thin rectangles, now I'm going to be adding infinitely thin circular discs, and then just stacking them so that they eventually create this object that we have. Yeah.
I know it kind of makes like a cylinder-like shape. Do we have to like use the volume formulas for shapes?
Right. So it looks like a cylinder, but eventually this curve is going to do all sorts of weird things, and is no longer going to fit a cylinder shape. I know this kind of looks like a cylinder, but it's also not like an exact cylinder. So, or this is not even a cylinder, right? Cylinder is going to be more like this. Right, so it's not a cylinder, it's not a cone. This is still not a geometric shape. So we're gonna have to rely on calculus. Okay. Okay. So that's what we're kind of working towards. Okay. So now we're still going to draw this distance from this dotted line. We call this dotted line axis of revolution. Which I'm going to abbreviate as AOR. And that's going to be the new center of this object. Okay. So we're still going to draw this vertical distance from the dotted line to the edge of the diagram. But now this is no longer the height of a rectangle. This is now the what of another shape. Radius of a what? Circle. Okay, so that's the big adjustment we have to make. We're still going to draw this vertical distance, but we're going to call it something else. Okay, rather than calling this the height of a rectangle, now this is going to be the radius of some infinitely thin circle, okay, which we're going to call R of x, or big R of x. Okay, there's going to be a distinction, uppercase R and lowercase r, or lowercase r. We're going to talk about that on Friday. But right now, we're just going to be calling this method only one radius, and it's going to extend from the center of the object to the outer edge. So let's look at one particular infinitely thin disk. So we're just going to look at one instance of it and kind of take one slice of it and just pick it apart. So we know that this is the radius of the circle, of the circular disk. I'm going to call R of x. The width, this infinitely thin width, is represented by dx, just like how The dx before represented the width of some rectangle. Now, what do you recall is the area of a circle? Pi r squared. Pi r squared. But we know that the radius of this disk is going to continually change, right? Over here, it's going to be shorter. Over here, it's going to be longer. And depending on the shape of the curve, it can be constantly changing. And so we want to represent that constant change of every radius of every circular disk with uppercase R of x. So I'm going to replace that radius squared with big R of x squared. So that represents the face of this disk, right? Pi r squared. Now area is how many dimensions? 2-dimensional, right? And then this dx, that width, is going to give it that third dimension, right? So area is 2-dimension, and we add in that dx, that'll give it that third dimension. And we want to accumulate all the differently sized disks from one end to the other, and that's where the integral comes in. So def integral from a to b, pi big R of x squared dx. Okay, so pi r squared, that's 2-dimensional, dx, that gives it that third dimension, and then we're accumulating all these differently sized disks from one end to the other. Obviously, we're not doing all this by hand. We're just identifying the important information, sticking to the formula, and then let the calculus do all the work for us. Okay. But if you notice, the information that we're going to gather is going to be virtually the same. We're still going to be finding that distance, but instead of calling it just top minus bottom, now the top minus bottom for a rectangle, now the top minus bottom will represent the radius of some circle, and we just have to insert it into a different formula. But we're gathering information still the same. We're still gathering the same bounds as if, like I said, we're finding area. We're still doing top minus bottom, like as if it was rectangles. It's just into a different formula. Does that make sense so far? Okay. All right, so let's look at this instance here. Let's see if we can find the volume of this particular object under the graph y equals square root of x. Okay. All right, a couple more things that I want to go over. The one that we're going to have an easier time with is going to be vertical radius when our radius is vertical, which is going to be a top minus bottom relationship, which is going to be just everything familiar with our functions. But if we're forced into a horizontal radius, then just like before, yesterday, we have to rewrite all of our equations. Our variables have to be adjusted to be in terms of y. And again, this is going to be the one that we're going to potentially have more trouble with. Okay, but we'll get to that. We'll start off with the easier one here. Okay, so we're going to be building a radius instead of some height, and the distance and the radius is always going to connect from the center of your object, the axis of revolution. I'm going to use a dotted line to indicate where the center of this object is going to be. It may be at the edge of the diagram, but we just have to imagine that we're going to rotate it around some axis. We're going to extend from the axis of revolution, the dotted line, to the boundary of our shaded region. Okay, so example 1, we're going to do this problem all over again, but now from a volume perspective. Find the volume of the solid rotated about the curve y equals root x around the x-axis between 0 and 4. So this around the x-axis indicate that y equals 0 is our axis of revolution. Okay, so here's our shaded region. So we're going to get the same shaded region as before. We're going to find the bounds the same way. We're going to build the vertical length the same way. It's just that we're inserting to a different formula because now we want to find volume of some object instead of the area of that shaded region. Okay, so everything that we've done before here, we'll do the dotted line around that x-axis. It looks like it's the edge of the diagram, but it's really the center of the final object, right? But just understand that sometimes the center of your object is going to be at the edge of a diagram because we're not going to actually draw it out and we're not actually going to reflect it all the way around. Okay. So this is the axis of revolution here. And from the dotted line, you're going to extend to the boundary. Okay. This is a good habit that we're going to build. I know right now it's obvious because there's no other place that you can extend from one into the other. But when we talk about subtracting out holes for a washer method, this is going to be a good habit that whenever you build anything radius related, start with your dotted line. Okay, that is going to be your anchor. From there, extend to wherever boundary you want to extend to. Okay, but always include the dotted line when you are drawing your radius. Okay, so before we called this the height of some rectangle. Now it's going to be the radius of some representative circle. So let's build our radius, big R. We're going to do this exact same way that we've done before. Top minus bottom, just like with rectangle. So what's the top of my radius sitting on? What's the equation of this graph? Good X, okay. Minus, what's the bottom of the radius sitting on? Y equals 0, so 0. Okay. And then our bounds is going to be from where to where? X values, right? We have to do X values. We can't try to pick a Y value there because everything that we want to insert into our formula has to be X values. So from 0 to 4. So now we just put into our formula. V is equal to. Now, typically what we do is we pull the pi out in front, even though it's pi r squared, but pi is like a coefficient. So we typically like to pull that pi out in front. It's not going to get impacted. It's really just the radius that's going to get impacted with the calculus. So we'll pull the pi out in front, definite integral from 0 to 4. Big radius squared. Now I can just drop the 0, right? So it's just going to be big radius squared. Yes. Okay. We're going to.
Does the square root cancel out then? If it's
It does. Yep, it does. So we're going to work this out by hand. In this case, they will cancel out. So it's just really definite integral from 0 to 4 of x dx. Okay, we'll do the calculator a little bit, but I think this is easy enough. We're going to do this by hand. So we'll solve for x. Well, x becomes what? X squared over 2. And then we can evaluate between 0 and 4. Upper bound first. What does that clean up to be? 8. And then we have to make sure we include what at the end? 8 pi. Yep. And this is now volume, so we have to just indicate units cubed, cubic units. So we're never going to have to draw the full object in front of us. We just have to be able to identify. But the idea is that the volume that we just found was for this object. This imaginary rotated bowl-shaped object that we're trying to create. Yeah. No, for this quiz, you're just going to be working on the setup. If you can do the setup, the calculator will do the rest for you. Okay. But you will have to use your calculator to find intersections potentially, and you may have to zoom in. You may have to find some certain features of it, but a lot of the calculus we can leave out because on the quiz, at least, I will let you use the calculator.
On the test bit?
Well, this unit will just be a quiz. Now, having said that, there are going to be some problems on the AP exam that will be asking you to do this without a calculator. And sometimes there is going to be use substitution involved where you got to work it out by hand. So we'll maybe do some practice with that when we get to our AP review. But we can't always assume that on the AP exam that every volume problem will be calculated. Okay. Or if it's too complicated for non-calculator, what they will ask you to do is they'll just ask you to do the setup, and they will not, if it's really complicated problem, they will make it either calculator or non-calculator and just the setup. But if something is manageable with use substitution, then it could be a non-calculator question where they're asking you to do the entirety of all the steps. So we'll see some variety within these problems.
So is there like a calculator section and non-calculator section on the AP form?
There will be, yeah, there will be. I would say about 1/3 of your exam is calculator, and 2/3 of it is going to be non-calculator. Yeah. Now, I do want to kind of talk about how you would enter this into the calculator. So you'll do Math 9. Okay, so right now, it may feel like overkill, but I just want to kind of set you up for what will be a common step that you can take to kind of ensure that you're being efficient. Is when you have your R of X, and once you build your R of X, you can go ahead and put that under Y1. But if you choose to put all this under the main screen, that's fine as well. I just want to show you one way that we can do it. So now if I have square root of X under Y1, I'm going to go back to my home screen. I'll do Math 9. Now, when you do your definite integral, leave pi out of your calculator. Okay? You're just going to add pi on your own at the end. But if you insert pi into the calculator, it will start giving you decimals, and it may not be as may not be as accurate as you would like for a presentation. So leave pi out of your calculator, and you can just add it in at the end because it's not going to change. So we're going to go from 0 to 4. And you're going to type in your radius, which is root x, and you're going to do alpha trace y1, and then you're going to do y1 squared. Okay, so that it will allow you to have, that way you don't have to square it on your own. You don't even have to use parentheses. You can just do y squared, and it's already taken care of. Your radius is already built into your y1, and now it's a really relatively clean function. Now, if you want to type everything in, that's fine. But when we get to washer method, when there's like multiple parts involved and your radius is messy, it's nice to type everything in and just be nice and clean without having to worry about, oh, do I need another set of parentheses when I can just type it in like this. Okay, so 8, just make sure that this is not the entire volume. This is without the pi in it. And then after you write that 8 down, you can add pi on your own. Okay, so that's going to be how I want us to, how I want to present it to you guys, and I think that will be an efficient way to use your calculator. Okay, let's go to the next page. Oh, sorry. One more thing I want to point out is look at your axis of revolution in relation to your shader region. Do you see any space at all between the axis of revolution and the shaded region? There's no space, right? Because the dotted line is right up against the flat surface of your shader region. There's no gap, there's no hole. So that's why we only have to rely on one radius. Okay, later on, we're going to see some potential gaps or axis of revolution up against a curved region. So if we see any space between the shaded region and the dotted line, there's going to be a different method involved to find the volume. Okay, but right now, I know right now we only have one scenario, but I just want us to kind of see that, okay, if you see a flat surface of your shaded region up against the dotted line, it's going to be this method. Okay, if it's not that, then it's going to be something else, which we're going to talk about on Friday.
Oh, that's a washer method.
That's going to be washer method. We're going to talk about that on Friday. Yeah, but the way that you can tell is the way the dotted line is in relation to your shaded region. That's how we can tell. Okay, and I'm going to keep pointing that out right now because it's all going to be flat surface up against the dotted line. But if you see any other situation, we're going to have a different volume formula for those scenarios. Okay, we'll do another top minus bottom one. Now the challenging part that we're going to that's going to be harder is going to be right minus left. So it says find the volume of the solid created by y equals 2 minus x squared. This is a parabola. You can graph it if you want, but this is just a parabola with a y-intercept of 2 that opens downward. And I forgot to add something here as well. It's created by the function y equals 2 minus x squared and the equation y equals 1 revolved about the line y equals 1. So there's another line that we have to sketch out. Y equals 1. So we're talking about this shaded region here. But we're also going to be rotating this about a line y equals 1. Again, I want to keep reminding us that your axis of revolution will always look like they're at the edge of the diagram, but in reality, it's the what of the diagram. Yes, it's really the center, right? I mean, we're not drawing out the three-dimensional object, but the idea is that after the shaded region gets rotated, it's going to look like a kind of like an egg-shaped object. Okay, so we're trying to find the volume of this egg-shaped object. Okay, we're gonna have to find the intersections of the shaded region, and that's gonna be what we're gonna need. We can use the calculator to find intersections, but I think we can also do this by hand. So I'm gonna solve this by hand here. So intersection, which will be our bounds. Sorry, 2 minus x squared is equal to 1. Okay, so subtract 1 from both sides. X squared equals 1. If I take the square root, x equals what? 1 and -1. Okay, so we know this is going to be a disk method. Rotating about this line, there's no gap between the dotted line and the shaded region.
What's that say?
Right here,
Like,
intersection, yeah, 2 minus x squared equals 1. So we're going to draw the radius. The radius is going to extend from the dotted line to the edge of your diagram, or the edge of your shaded region. So let's build our radius, big R. Okay, what's the top of the radius sitting on? Which graph? It's touching this curve, right? What's the name of this curve? It's the top of the radius sitting on. Or how about if I drew the radius over here, would that be easier to see? Yeah, it's the curve, right? So 2 minus x squared is the top graph. Minus, what's the bottom of the radius sitting on? Y equals 1, yeah. Okay, do we see that? We just have to build some relationship between the top and the bottom so that the formula, the radius, can adapt to the ever-changing radius for all these infinitely thin circular disks. Okay, what is this going to turn out to be? R of x equals 1 minus x squared. Okay, so I think we have everything that we need to build our volume formula here. So V equals I, definite integral from -1 to 1. Big radius. We gotta do it with big radius. Make sure we. Okay. What else? Can we just say dx, or is there something that we need to as well? Square, right? Because we're talking about radius, we're talking about a circular shape, so there has to be a circle area built into this formula, pi r squared. Okay, I'm just going to go into y1 and change to 1 minus x squared. Not going to graph it. I'm just going to use it for my volume formula here. Second mode, I'm just going to go back to the previous entry that I did. I'm just going to go up arrow on it, hit enter. And really, it's just the same format there, right? I'm just changing my bounds from -1 to 1, so that can save some time. But it's still going to be my radius squared. I just have my radius stored under y1. Now, we always want to see if we can try to force it or make it, see if we can change it into a fractional value. If it can't, then we'll just round it through decimal places. But if it can, that can be a little bit cleaner. So you can do math fraction. And in this case, it's able to get to a fraction for us. So our volume is going to be 16 over 15, what? Pi, good. And it's a three-dimensional object, so three-dimensional calculation, so units cubed. Yeah, I did not change that y1 because I went into y equals and I changed my radius there. Okay, top minus bottom, I think, is pretty straightforward. Let's look at something that is a bit more challenging, and that is, what if our axis of revolution is no longer horizontal? What if it's vertical? So let's look at some examples here. So it's given the region is formed by the function, the x-axis and the y-axis, and the graph given. Find the volume of the solid formed by revolving the region about the y-axis. So now we have a different line of rotation. So the y-axis, that's basically x equals 0. And first, let me just do the shaded region here. And here's my dotted line. Okay. This is really the center of my new object. If you kind of, again, we don't have to worry about graphing it. I just want us to kind of at least try to visualize it. What is this object going to end up looking like after full rotation?
Yeah.
Not a cylinder, but a what? No, it's going to be circular. The cone, yeah. You see that? I know it's maybe hard to see. That if we were taking this and we're rotating all the way around, it's going to kind of create this circular shape around this axis. It's going to eventually come out to looking like a cone. Again, it's not necessarily important that we know the shape. I just want us to make sure that we understand this is really the center of the object. This is not the edge of the diagram. This is really, our axis of revolution is really going down the center. But we're only seeing half the object or a portion of the object because we're not drawing the whole three-dimensional shape out. Okay, next up, do you see how the shaded region is right up against the axis? There is no gap. This is going to be this method. I know we're only doing this method right now. We're not going to see any gaps until Friday, but I want us to at least visualize it, because later on, you're going to have to be able to decide, wait, is this method or is this washer method? And we need to be able to recognize it by looking at how the dotted line is in relation to your shaded region.
Like quiz will be like that too.
Yeah, you're not going to be told if it's disk or washer. You're going to have to decide on your own. Now, we're going to draw our radius. Now, how is our radius going to look? How it's going to be different than before? Okay, so before we were extending from the radius, axis of revolution to the shaded region, and it ends up looking like a vertical radius. But now, if we extend out from our axis to our shaded region, it's going to be what orientation? Horizontal. So now we're going to have to imagine we're adding infinitely thin circular disks from the bottom to the top. They're going to be stacked vertically. Now, if we see anything horizontal, whether it's a radius or a rectangle, we have to spend the time to do what? Can we use the equations given to us? No, we have to rewrite it. Okay, we have to spend the time to rewrite it. So I got to solve for a different variable. I got to solve for x. So if I rearrange it, x plus y is equal to 1. If I add that x over, this linear equation is really what? X equals what? 1 minus y. So look at that form there. X equals, the right side is ready for me to use for my formula. What is the equation of this line here? X equals 0. We're also going to use this as well. Anything x equals indicates it's going to be a good form for us to do right minus left. Okay, let's build our radius. Now it's no longer r of x, it's r of y. Radius in terms of y. So what's the right endpoint of my radius now sitting on? 1 minus y. What's the left endpoint of my radius sitting on? 0. 0. So minus 0. It's always right minus left, or top minus bottom. We're always subtracting between our two endpoints. Now this reduced to just be 1 minus y. Okay. Where do you think our bounds are going to be? Is it this one here? It's the one up here, right? We have to do y values. I know if we made the mistake, we would still be correct, but it's not always going to be like this. We have to make sure we're looking at the right spots there. The lowest y value to the highest y value. Okay, so now let's build our volume. V equals pi, definite integral from 0 to 1. Big radius, 1 minus y. We got to make sure we do what with that? Square, and then dy. Good, dy. Okay, so then you will enter this in the calculator. You would not put pi in it, but you would use what instead of y? X. Use x in your calculator, even though on paper you're going to write y. Okay, so after all that is said and done, I'm going to skip to the end here. It ends up giving us 1/3 as our answer. And we have to make sure we include pi and then units cubed. Okay, let's do one more here. Why don't we try this on our own, and I'll work this through with you, or I'll work this through after you guys started. So it's the same idea, rotating about the y-axis. Very similar setup as before. And there's a need to rewrite your equation as well. Yeah.
Is that x equals 0 or x equals the red?
Oh, this is 0.
0.
Yeah.
We don't have to know exactly what the shape is when it's turned around.
We don't have to know the shape. Yeah, I just want us to understand this is not the edge of the diagram. This is the center of the diagram. And that's why we call it the axis of revolution. It's where the center of the rotation is going to occur.
It's kind of like someone cut a piece of.
Right. It's just like a two-dimensional cross section of the object.
This is how most of them are going to show up as.
Yeah, yeah, they're all gonna be two-dimensional shapes. We have just had to get the information and put into a volume formula. You're never gonna have to do any graphing or visualization to visualize it.
Regardless of the method, right?
I'm sorry?
Or regardless of the method, right?
Regardless of the method. Yeah, that's right. Yeah. Okay, can we tell this is this method? Because we don't see any gaps between the shaded region and the dotted line, right? It's right up against it. So flat surface up against dotted line, always going to be this method. What's my new adjusted equation going to be for my curve? Yeah, root 4 minus y. Now, technically, there's plus or minus, but the negative 4 minus y is going to be over here. We're only talking about the first quadrant, so we're going to take the positive square root of 4 minus y. Okay, let's build a radius. Right minus left. What's the right endpoint of my radius sitting on? Okay, the left endpoint is sitting on the 0. There's our radius. Okay, what bounds are we going to use? 0 to good y values, right? If we want to do right minus left, everything we put in has to be y. We can't mix x's with y's. Okay. Big radius. Make sure you square it because we need to have an area, circle area built into this formula somewhere, right? If we lose that square there, then we're no longer doing pi r squared. Then this is another different shape. Okay. We put this in our calculator. Leave pi out of your calculator. You're going to get a numeric answer, and then just add pi or include pi in your final answer. Okay, tomorrow we're just going to practice with this method. You guys have homework tonight, so check your calendar. All right, come get your phones. Okay. Thank you. Why one needs to be, remember, you can't use, I know you want to use the equation, but it's right minus left. You have to adapt to the different equation. Do root 4 minus x.
Okay.
Sorry to ask. Yeah. Oh, it's my teacher speech too. It's okay. And it's just, do you know Miss Johnson?
Yeah, I'll drop it off in the mailbox. Okay, thanks.
There's no shame.
Good, how are you?
Good. Well, I just want to let you know, I'm not gonna be here Friday when you go over that new method.
Yeah,
I'll be at- We're sure.
okay, yeah, I'll put the recording on the website. Yeah,
Can I come a little bit early tomorrow, like to review?
sure, yeah,
Alright.
sounds good.
I don't want to get behind, so.
Yeah, sounds good.
It's fine. I've come and we could go over the text I took yesterday. Because I'm,
Tomorrow morning?
yeah, tomorrow morning, because I have an econ,
Okay,
but,
maybe advisement, tomorrow advisement. Okay, sounds good, yeah.
So you contest? Anybody get it up? Oh, okay. So thank goodness for that. Hope it never, it's so fun. Yeah, it was quite honest.
So it's Wednesday on Monday.
Yeah. People say like banknotes, like, what he's gonna have to go over banknotes.